All right, here we go. Section 6.3, pre-calculus, instructional YouTube video talking about vectors and arithmetic with vectors. So basically add, subtract, scalar multiplication, unit vectors, the IJ form, direction, angle, magnitude, and we'll throw a word problem in at the end. Okay, so we're going to start off with this problem where we have two vectors. We've got vector u, the vector u's component form is -4, -3, and vector v has component form 5, 7. And we're going to find 3 vector u, we're going to find -2 vector v, we're going to find vector u plus vector v, 2u minus v, oh no, 2v minus u, sorry. Switch it up on you here. 2v minus u. And let's throw in magnitude of v at the end here. We'll have some more, but this will be enough for this space here. Okay, so in order to do a scalar multiple, all this is it's a number times a vector. The answer is going to be a vector. And it's just 3 times -4, -3. And we just multiply each component by 3. So we get -12, comma, -9. That is our new vector 3u. Basically we had this vector here, 1, 2, 3, 4, 1, 2, 3. And now it's just same direction, 3 times as long. All right, let's look at b, which is -2v. This is going to be -2 times 5, 7. Now, if we multiply by a negative scalar, what's going to happen is it's going to double the magnitude, double the length of the vector, but it's going to switch the direction. So, because these are both positive, they're both going to be negative when we multiply through the vector. So we get -2v equals -10, -14. It has the opposite direction, right? Instead of going positive, positive, it goes negative, negative. And it's got twice the magnitude. All right, if I have u plus v right here, that's the next one. U plus v, we have -4, -3 plus 5, 7. What's happening here is we're just going to add the components together. We're going to add the x parts together, we're going to add the y parts together. This is algebraically how we do it. So -4 plus 5 is 1. -3 plus 7 is 4, 1, 4. Now we can look at this graphically as well. I've got vector 5, 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. And I've got the vector -3, or sorry, -4, -3. 1, 2, 3, 4. 1, 2, 3. Now what I can do is I can go on either vector. So I can go at the end of the 5, 7, and I can just copy this -4, -3 and paste it on the end. I can go -4, 1, 2, 3, 4. So it would go to here, right? Because this was actually supposed to go to 5. And then down 1, 2, 3. I know they look weird. This should look exactly the same as that. It doesn't because I'm drawing it on a whiteboard. Or I could start at the end of this vector and just add the 5, 7 up. So I'm going to go 5 to the right, 1, 2, 3, 4, 5. And then I'm going to go up 7, 1, 2, 3, 4, 5, 6, 7. Boom, look, it goes to the same spot. That spot is the resultant vector, which would be at 1, 4. It's to the right 1, 1, 2, 3, 4, up. Okay. let's look at 2v minus u. So 2v, well, that's just written right there. 2v is going to be 2 times 5 comma 7. And then minus u is going to be like plus -1 times -4, -3. So 2 times 5, 2 times 7 gives me 10 comma 14 plus -1 times -4 is 4, -1 times -3 is 3, right? And then just add the x's, add the y's, add the components. So 14 comma 17 would be the answer here. All right, magnitude of vector v. To find the magnitude, we're just finding the length of the directed line segment. We're at 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. This is our vector v. To find the magnitude, it is this length, right? If we look at it, we have a right triangle, 7 for the y, 5 for the x. The magnitude of v squared is 5 squared plus 7 squared, or the magnitude of v, and we're just using Pythagorean theorem here, is the square root of 5 squared plus 7 squared. And it's always going to be this way. The magnitude is always going to be the square root of the sum of all the squares of the component. So square root, that thing squared plus that thing squared. So here it's square root 25 plus 49, which is square root of 74. I don't think 74, let's see, that would be, let me just double check this. 30, 74, blah, blah, blah. Nope, I don't think 74 has any perfect squares in it. We're good, it's just square root of 74, that's it. So, that is magnitude of v. All right, let's do a little bit more work with these vectors and then we'll go from there. So, knowing what the magnitude of v is, oh, sorry, never mind, scratch that. Knowing how to find the magnitude of v, go ahead and find the magnitude of 3u. So just do that on a piece of paper while I erase the rest of this stuff. So here, if I'm finding magnitude of 3u, I'm going to find the magnitude of 3 times -4, -3, right? Which is the magnitude of -12, -9, which is the square root of the sum of the squares. So -12 squared plus -9 squared. Doesn't actually matter if you use a -12 or a -9. You can do +12, +9. Because squaring a negative is the same as squaring a positive. Right? We're going to get square root of 144 plus 81. Square root of, what, 5 to 225? And that is 15. Boom. Now, if we look at this, if I find just the magnitude of u, right, that is the square root of 3 squared plus 4 squared, negative, but the negatives don't really matter, which is 5. The magnitude of u is 5. The magnitude of 3u is 15. So 3 times the magnitude of u is the magnitude of 3u. This is something that will always be true. Now, let's look at what about if I take the magnitude of u plus v. Well, remember we found u plus v, right? U plus v was 1, 4. We did that before. So if we do the magnitude of 1, 4, it's going to be the square root of 1 squared plus 4 squared, square root of 17. Now, is this the same as magnitude of v plus magnitude of u? Is it the same? Well, we already know magnitude of u is 5. Magnitude of v is what, 25 and 49, oh, what was that? 74? So square root of 74. This number is bigger than that number, not the same. So it's important to know when you're dealing with magnitude, multiplication, scalar multiplication with a magnitude, that works either way. 3 magnitude of u is the same as the magnitude of 3u, but the magnitude of the sum of two vectors is not necessarily equal to the sum of the magnitudes, not equal. Sometimes it will be, rarely. Like if one of these is a 0 vector, sure. But it's not going to work that way. Okay. Let's find the direction angle of u, and then we'll talk a little bit about direction angles in different quadrants other than vector u. All right, so if we're looking at vector u, we already have the magnitude. The magnitude of the vector u, let me just sketch this out, so get rid of this a here. U is -4, -3. Ah, rats. There we go. And that's here. 1, 2, 3, 4. 1, 2, 3. That's vector u. Right? We can describe vector u in component form using that -4, -3. Saying wherever the initial point is to get to the terminal point, you go 4 in the negative x direction and then 3 in the negative y direction. Boom, you're at your terminal point. That's what this -4, -3 means. We can also describe it using its magnitude, which we already said was 5, and its direction angle, which we're going to denote theta sub u. It's got a little subscript u, saying that's the theta for u. This is, so it's kind of like if we had a circle of radius 5, this angle here tells us where on that circle our vector ends up, points to. So this theta sub u is this angle here. The direction angle always starts at the positive x-axis and goes counterclockwise, just like on the unit circle. So to find this, what we do is we look at this triangle here, and we look at the reference angle, right? Because this orange is theta sub u. If I look at this reference angle, alpha, and I look at the right triangle with that reference angle, what I can do is I can say I've got 3, 4 alpha. Don't worry about the positive negatives when you're just looking at the triangle. And I say, aha! SOHCAHTOA, remember that old thing, right? Tangent of the angle equals opposite over adjacent, or the angle equals the arctan or the inverse tangent of opposite over adjacent. Plop that in the old calculator, making sure that you are in degree mode, because we're talking degrees here. So tan inverse, we get about 36.87 degrees. 36.87 degrees. That's alpha here. That's not our direction angle. Our direction angle is this big orange angle. So this big orange angle goes into quadrant 3, which means it's more than 180. How much more than 180? 36.87 more than 180. So for the direction angle, you find your reference angle, alpha. In quadrant 1, alpha and theta are the same. In quadrant 2, if you had an angle like this, this would be your alpha, this would be your theta. It's going to be 180 minus alpha equals your direction angle. Quadrant 3, we have an angle like what we have there, right? Alpha's here, that's theta. Theta equals 180 plus alpha. That's quadrant 3. There we go. And if you're in quadrant 4, let's say you're down here, this would be your reference angle alpha here. Theta is going to be 360 minus alpha. There you go. Boom. So for this one, we're in quadrant 3. So our reference angle is 180 plus 36.87. So we got a 0.87 at the end here. We've got a 6 and a 210, right? Yeah. About 216.87, right? And yeah, 3 and 18 make 21. Boom. Cool. So this angle, that magnitude. This gives us the same information. This is more exact because this number is rounded, the angle is, but if we use the exact angle, like if we used arctan of 3/4 as our reference angle instead of the decimal approximation, it would give us the exact same point. Okay, cool, we got that. So what we're gonna do now is we're gonna talk a little bit about the IJ form for vectors. So we talked a little about how, we can describe a vector using component form, right? Component form is x number, comma y number from the origin. We can have magnitude and direction angle, which basically tells us on the graph what angle to go about and the length. Right here, component form is like x, y, coordinates. Magnitude, direction angle tells you the length of the vector and where it is with respect to what angle from the positive x-axis. We can also have it as a linear combination of the vectors that we call I and j. And that's what we're going to talk about now. And this is basically, it's almost the exact same thing as component form. It's just more convenient in some fields of mathematics or when you're doing other problems. The IJ form is more convenient. Sometimes component form is more convenient. The nice thing here is when we're talking about vectors right now, not when we get to 6.5, but when we talk about vectors right now, we're talking about all real numbers. We can also use vectors to denote complex numbers, which we will do, but not right now. So this I is not the imaginary number I. I represents the unit vector in the x direction. So it's just 1, 0. J represents the unit vector in the y direction. And we can rewrite any vector that's written in component form using the linear combination of I and j, or the IJ form. So let's say we have a vector like 3, -5. What I can do is I can say this 3 is 3 of these 1 zeros, because it's 3 x's, And then this -5 is -5 of these 0, 1s, right? Because I have like 3 in the x direction, -5 in the y direction. Or I can just say 3i minus 5j. This is exactly the same. These mean the exact same thing. It's just a different way of writing it. Oh yeah, and if I had something like this, 8i minus 10j, well, that's just 8 comma -10. If I had something like this, -3i plus 8j, that's just -3 comma 8. That's it. So the I is denoting the x, the j is denoting the y. Cool, let's do a word problem. All right. Word problem time, yeah. Word problem, word problem. Here we go. I need a pen that's going to be able to write stuff and not go all dry on me. Let's use, ooh, this purple one should be good. All right, we have two forces with magnitude. So we have some forces with magnitudes of 578 newtons and 650 newtons are acting on a machine part. Yes, this is kind of a physics problem, but it's like physics light. At angles of 60 degrees and 135 degrees, respectively, blah. Right, this 60 is with the 578, this 135 is with the 650, right? Those are those angles for those. So these angles from the positive x-axis, what we want to do is we want to find the direction angle and magnitude. Find direction angle and magnitude of the resultant vector. The resultant vector is the sum of the two vectors, what you get when you add those two vectors together, or in other words, what you get when you have both of those forces pulling on that machine part. What is the total sum of the poles? What is that sum force pull doing? All right, so let's just look at this. Let's say we have this machine part. It looks like this. I don't know, let's say. And we have a 60-degree force. The 60 degrees is 578 newtons. And this angle here is 60 degrees. And then we have a 135-degree angle with 650 newtons. Oh, that shouldn't be degrees, that 578 should be newtons. And newtons are just so newtons are a measurement of force, kind of like pounds. So 650 here, and then the angle is 135 degrees. All right, so you'll notice each force is pulling up. Boop, boop. One's going to the right, one's going to the left. So let's see what the resultant force is. The way to do this is we've got to add these vectors together to get the resultant force. To add them together, it's going to be easiest to put them in component form. So I'm going to take the purple vector, I'm going to call it V. Why? Why not? And I'm going to take the orange vector, and I'm going to call it U. So I'm going to find the component form for vector V. Vector V is, well, it's going to have an X. So if I look at this, right, I've basically got this sort of thing going on here. I have 578 newtons, and I have a 60-degree angle here. I want to know my x and my y. Well, if I want to find that, I would use sine of 60 to find y. Right? Sine of 60 would be y over 578. Whoa. Sine 60 equals y over 578. I would just multiply by 578. Plug it in and get whatever 578 times root 3 over 2 is. Which is about 500.56. So that's my y, 500.56. Approximately, that's what my y is. And then to find my x, it's just going to be 578 cosine 60. That's going to be my x component for v. And actually I would call this v sub y and v sub x, saying it's vector v, x and y. And 578 times cosine 60 is going to be 289. Exactly. Remember, it's like the 1/2 root 3 over 2, 1. Right, so it's a 30, 60, 90 triangle. So we have 298 and 500.56. Those are the components for vector v. Find the components for vector u. What we can do is we can say, this is the same thing as this problem, except instead of having a 60-degree angle, I have a 135-degree angle. And I'm going to take a little aside here and just tell you something. If we ever have a direction angle and a value or magnitude, because that's this force right here, the 650 is the magnitude. If I want to find the component form for this, what I do is I just imagine it's on a circle with a radius of 650 degrees. Oh my goodness. A radius of 650, not degrees. And it's at an angle of 135 degrees. If I wanted to find the corresponding point on the unit circle, I would just go cosine 135, comma sine 135. But that's on the unit circle. I want it on the 650 radius circle. So I just multiply each thing by 650. So what I get is the x for u. So the x is 650 cosine 135, and the y is 650 sine 135. Right? Remember, sine 135 is going to be root 2 over 2. Cosine 135 is negative root 2 over 2, because 135 is like 3 pi over 4. All right, so 650 cosine 135. That gives us negative 459.62. I'm just rounding to the 100th, negative 459.62, comma, and then it's going to be the same but positive here. I mean, now you can plug it in if you want, but 459.62. All right, so I have my component form for u, my component form for v. What I'm going to do now to find the resultant vector is I'm going to add u plus v and see what I get. So here, negative 459.62 plus 289 is going to give me negative 170.62, and then 500.56 plus 459.62 is going to give me 960.18. And if we think about that, it makes sense. There's going to be a little bit more pull to the left than there is to the right, and there's going to be a lot of pull going up. Both vectors are pointing up, so yeah, there's going to be a vector going up more so, and not as much to the left. All right, but it's not asking for this, it's asking for the magnitude and direction angle. So we can just look at this, right? Basically, we have a vector like this, negative 170, right? Negative 170.62, 960.18. If I want to find the direction angle, I'm going to find alpha right here, and I'm going to go 180 minus alpha. So the direction angle, theta sub whatever, u plus v, is 180 minus alpha. Alpha here is going to be the inverse tangent, the arctangent of the opposite over the adjacent. So 960.18 divided by 170.62. Get rid of the negative, I just want that alpha to be positive. Doesn't matter if it's negative or positive. I'm taking care of the negative by going 180 minus it. If you get a negative number, right, if you use negative here, you go 180 plus that negative. So tangent inverse, 960.18 divided by 170.62. Boop. There we go. 79.92 degrees. So we're going 180 minus 79.92. Which gives us about 100.08 degrees. That's the reference angle, sorry, not the reference angle, that is the direction angle of the resultant vector. And then to find the magnitude, right, it's just going to be the square root of the sum of the squares. So negative 170.62 squared plus 960.18 squared. Just going to put that in the old calculator here and hang with me. 0.62 squared plus 960.18 squared. And we get about 975. And that's going to be 975.22 newtons because our magnitudes are in newtons. We're talking about a force here. So the sum of those forces is going to be, or the resultant force has a magnitude of 975.22 newtons at a direction of about 100 degrees off of that positive x-axis, which makes sense that it's mostly going up and a little bit to the right from the diagram. All right, hopefully that was enough information for you. Real quick run through of this problem. What you do, it's helpful to draw a picture, find the component form for each one. Remember, you can go magnitude times cosine of the angle for your x, magnitude sine of the angle for your y. Got your component forms, add them together for the resultant vector, go from there. Thank you for watching. Have a wonderful day. Good luck on the homework.